to talk a little bit about our research activity, and in the afternoon, I would like to invite two students in my laboratory, and they will give some topic. They are one is from China, and another one is from Taiwan. So I expect them to give you a talk in Chinese.
Chinese. Thank you.
I expect so. Maybe I know there are two non-Taiwanese students in here. So this is the menu I prepared. So first 1 hour, I will give a small talk of our research activity, and from 11, let me introduce our young assistant professor, Dr. Koshiba. He will give you another topic, quite different from mine. And from 12, please have lunch. I prepared Japanese lunch box for you.
Yeah.
Today and tomorrow.
Thank you.
Okay. And from 1 p.m., two students will give you a presentation. And unfortunately, I prepared originally 3 students, but 1 student have some small trouble, health condition.
So maybe our students can share something.
So you mean the presentation from students?
If we have time.
Yeah, we expect your presentation from you tomorrow.
Tomorrow?
It's okay.
Okay.
How many person?
Okay.
How many person we have to present? How many people we have to present?
Only you.
No, not me.
You are the best.
We can be flexible.
Okay.
And from around 2 p.m., I will show you around our laboratory. Unfortunately, today the weather is very good. The temperature of the laboratory will be very high. I will show you around here our laboratory. So today, now I would like to a little bit talk about experimental studies on inhalation disasters in Ujigawa laboratory. So I'm now a professor of DPR Kyoto University, but since I was a student, I have been studying inhalation disasters due to heavy rainfall. So I would like to talk a little bit about our study research activity. I divided my talk into 4 parts. The first part is a brief introduction of Ujigawa Auto Laboratory. And second one is outline of inhalation disasters in Japan. Yesterday, Professor Sayama also talked a little bit about this topic, flood disasters in Japan. And third one is study on fluvial inundation, and fourth one is study on pluvial inundation. So, do you know the difference between fluvial inundation and pluvial inundation? The fluvial inundation is caused by the flood water of the river due to overtopping or tide breach. On the other hand, the pluvial inundation is caused directly by the heavy rainfall. So, brief introduction to Ujigawa laboratory. This is the aerial photo of our laboratory. Okay, so as we know, Kyoto University has 3 major campuses. And first one is Yoshida campus. Maybe last week you visited this Yoshida campus, Professor Fujibara. And second one is Fuji campus. Yesterday you visited. Yeah. And most of the TBR laboratories are located here. So I and Dr. Koshika also often go to Fuji campus to have meetings or some activities. And the third one is Katsura campus. And most of the graduate school of engineering are located here. So we are cooperative members of graduate school of engineering. So I sometimes go to Katsura campus for lectures. So yesterday morning I gave a lecture at Katsura campus. After that lecture, I joined the Fuji campus yesterday. I'm not from here. So today you kindly came here, Ujigawa Open Laboratory. The location is here. Ujigawa is the name of the river in front of this laboratory. Name of this river, Ujigawa. So of course, our Ujigawa Open Laboratory belongs to the TPR. Yes, so this is the photo of Ujigawa Open Laboratory. We have 4 major buildings for the experimental facilities in level 1, 2, 3, and 4. And now you're here. So, this building was constructed 10 years ago. And total area is almost 70,000 square meters. Almost 70,000 square meters, and there are 3 research sections. That makes them 3 laboratories, and 3 professors, and full professors are working here, and including Dr. Koshiba, totally 6 professors, including associate professor and assistant professors, are working here, and almost approximately 30 students are also studying in this laboratory, and this laboratory is widely used for academic research activities of other universities or other research institutes in Japan. And also these facilities are open for special trainings for residents and broadcasting or firefighters and policemen. So we have several unique facilities. So in this afternoon, I will show you these facilities, some of these facilities. And so some of them, if you like, you can experience
Raining.
reading or some other activities. You can expect them. Okay, so this is the photo of the open campus day for citizens. This is the big event once a year, open for the local residents. And this is a small experiment of the debris flow. And this is the staircase. This staircase is assuming connecting the ground surface and the underground space. So they are trying to evacuate from the underground space on the ground surface. And he is the father of her. So this is most popular activities of this facility. And this is rainfall simulator. And this is the tsunami wave generator. And maybe you don't know what they are doing in this photo. They are waiting for this activity for 1 hour. So they have been waiting for a very, very long time.
For 1 hour.
Yes, for 1 hour.
A lot of people and only 1 hour.
Oh, cool.
I mean, a lot of people and only for 1 hour.
Another, so sorry.
No, I mean that a lot of people, but only 1 hour to experience.
No. So at the time, there were several opportunities to experience this one. So that time, opening time is determined. So they were waiting for this activity. And another time they can experience this one, also this one, also this one. Now we changed the system, and they have all the participants have to make reservation in advance. So we cannot find this phenomenon now. Okay, so the research mission of this observatory is various topics of the disasters caused by the heavy rainfall from the upstream to the downstream of the river basin area. So, for example, the river Oslo and the river Bridge area variation and urban inundations. So these topics are also contained in our research activities. Okay, so next week, the outline inundation disasters in Japan. And first of all, I would like to show you this slide, comparison between Japan and Taiwan. I know Taiwan is an island country, and Japan is also an island country, but the length and river basin area is a little bit different in Taiwan and Japan. But the highest amount, the Taiwan's highest peak is higher than Mount Fuji. And of course, the annual precipitation also will have more rainfall than Japan. So that means totally the natural condition in Taiwan is severer than Japan because you have a lot of more rainfall and steep slope of the riverbed in the river basin area. So I would like to show you that the difference between Japan and Taiwan. And this is the annual change in Japan. And the blue color is the casualty caused by the water-related disasters from 1946 to 2019. So just after the World War II, we had a lot of casualties, more than 1,000 people. If you feel cold, please, you can change the temperature. And we can find more than 1,000 people who were killed just after the World War II. But after the 1960s, the number of casualties gradually decreased. On the other hand, the red color means the amount of damage. So, of course, the amount of 100 yen has changed from this period and this period. But here it looks gradually increased. But this graph means that the amount of damage has not decreased. Obviously, these 15 years. So the number of casualties decreased. That amount of damage has not decreased. And that means the urban area are mainly damaged, where a large amount of asset is located. We can understand this kind of phenomena occurred during these 15 years. And this figure shows the ratio of the pluvial inundation and the fluvial inundation amount of damage to the whole nation area. And about 40% as a pluvial inundation accounts for 40% of the amount of damage in the whole nation area. On the other hand, if you limit the amount of damage in the Tokyo metropolitan area, that means the highly urbanized area. More than 70%, the pluvial inundation accounts for more than 70%. So pluvial inundation is a major disaster of the rainfall in the urbanized area. And of course, we have more and more heavy rainfall. And this figure shows the frequency of observation of more than 50 millimeter per hour rainfall. Also, from 1976, from 1976 to 2024. And gradually, the frequency of observation of more than 50 millimeter per hour rainfall is increasing gradually. And this figure shows the frequency of the observation of more than 200 millimeter per day rainfall. Also, this a little bit long-term rainfall, heavy rainfall is also gradually increasing. And that's why we find severe inundation disasters everywhere, in many places in Japan. And for example, 5 years ago, we had a severe inundation disaster in Kumamoto area. And this is the river name of Kuma River. River is from here in this direction, and on both sides of the Kuma River severely inundated. And this is the estimated inundation area. Blue colored area is the estimated inundation area. Just like the river width is increased 1 kilometer. Just like 1 kilometer, very wide river was flowing along the Hitoyoshi city. And also the many small tributaries also caused a lot of inundation disasters. This is the elderly persons facility, and here totally 14 people were killed here. And in 2019, Typhoon Hagibis attacked the eastern part of Japan. And one of the characteristics of this disaster was, and we found a lot of dike breach, more than 140 dike breach occurred in eastern part of Japan. This red cross means the location of the dike breach. And blue color is the river directly managed by the national government. Even the principal rivers, we found dike breach. And this is this location. This photo is this location of the dike breach point here. And caused by this dike breach, in addition, a lot of Shinkansen cars are submerged like this. We had very severe damage. And this is the disaster that occurred in 2018. So totally more than 200 people were killed by these disasters. And this kind of dike breach occurred, and also a lot of debris flow and sediment related disasters occurred also. This. This is another example of that disaster was occurred in 2017. Northern Kyushu area. They had 800 millimeter during 12 hours. 800 millimeter rainfall. And that heavy rainfall caused severe sediment disasters, not only the rainwater, salt water, but also the sediment and driftwood deteriorated the river basin areas like that. And you can find a lot of driftwood among the houses. So totally more than 40 people were killed at the disaster. And in this way, so we have a lot of inundation disasters, many places in Japan. And how about the Kyoto? Also in Kyoto, we have inundation disasters. So I found this kind of phenomena, overflow from the manhole. This movie was captured by me. Yeah, I lived very close to this location, and I I recognized a very heavy rainbow. So I walked around my house and accidentally I found this phenomena. Wow. This morning, did you use the KR railway?
Yes.
Railway, 中枢道.
中枢
中枢道 station. Yes.
中小
Yes, yes.
中小
中枢道 station.
Yes.
And this is the ordinary photo, but during the typhoon season, totally is
Totally submerged.
Totally submerged. No, I can find a very big bus.
3 meter.
4 meter.
4 meter.
Yes. Below the railway, the depth is 4 meter. Height is 4 meter, but this underpass was totally submerged like this. And during this typhoon, one of the most severely damaged area is here. In this area, here is one small river, and here is one tributary here. And usually, if the water level of this river increased, here is one gate, and gate is closed, and this pump station will drain the flood water of this small river tributary. But accidentally, at the time, this pumping system stopped by some accident. So this area severely inundated, more than 2 meters. This is my former boss. His height is 1.7 meters. While the maximum height is 2 meters. So in this way, this area is usually protected by the pumping system, but pump could be stopped by accident. So in that case, we will suffer from such severe inundation disasters. Yeah, so in this way, we have a lot of inundation risks in many places in Japan. So the inundation disaster, the protection of the inundation disasters is a very main topic of our research activities. So now I would like to talk a little bit about study of fluvial inundation. We have several facilities, experimental facilities in our laboratory, and one of them is the hydraulic model of overland inundation. Here, this is the hydraulic model. The size is 10 meters and 20 meters. 10 meters and 20 meters. And this is the model of the actual Kyoto City area. Kyoto City, central part of Kyoto City. And this is the Kyoto Imperial Palace. And Kyoto University is here. Kyoto University of Yoshida campus.
We live, last week we lived next to the Emperor House.
Next to this.
Yeah, next to our hotel.
Oh, your hotel is close to Imperial Palace. Okay. Yeah, and this is the other Kyoto City model of this area, 1 kilometer and 2 kilometers, including Shijo Street and Kyoto City Hall area. And here is one major river in Kyoto City, Kamogawa. Kamogawa is from here. So we assume if the flooding from the Kamo River occurred in Kyoto City area, what will happen in this area? And so we carried out these experiments about 20 years ago. Here is the Kamo River, and the flooding will start from here. The Kyoto City topography is tilting from north to south gradually, so the inundation water will flow mainly in this direction. And we carried out the numerical simulation of this reproduction of this experiment. This is the computational meshes used for that numerical simulation. We divided the street area and residential block area by using these computational meshes. So we compared the results. This is experimental result of the inundated area of about 1 minute later, 2 minutes later, 3 minutes, and 5 minutes later. And this is simulation results. So we can find some difference, but that is acceptable, I think. And also we compared the time change of the inundation depth at several points. And in this figure, in this slide, I showed the 4 points. At this point, we obtained a very good agreement in the experimental results and the simulation results of the time change of the inundation depth. So in this experiment, we assumed only inundation on the street area. But actually, in the actual situation of the inundation, the inside of the building also will be inundated. Okay? But in the existing research, usually we will ignore such inundation inside of the building. So, usual inundation model, we assume this kind of time change of inundation. Okay, that means no inundation inside of the building because it is very difficult to validate such a numerical model with comparison of the experimental results. You can easily imagine it is very difficult to carry out the experiments considering the inundation of the inside of the building. So we usually ignore the inundation of the inside building. On the other hand, Japan's central government has some manuals of the simulation model of inundation. In that simulation manual, Japan's central government, they recommend the inundation also should be considered on the inside of the building. But according to that simulation manual, the water depth of the inside and outside of the building should be instantly the same. That means this kind of phenomenon. There is no difference inside and outside of the building. But actual phenomena, that is different. Firstly, outside of the building is inundated. After that, inside of the building also gradually inundated. Gradually inside of the building is also inundated. We would like to reproduce this kind of phenomenon. So we tried to carry out such experiment using this facility. So we removed all the city model, and we focused on this only small local area. We picked up these 12 residential blocks, and we reproduced individual buildings. Why only these 12 residential blocks? Because of limitation of the budget. But it is impossible to reproduce this the shape, detailed shape of the buildings. So we divided all the buildings into 7 categories. Using the ratio of 2 sides, north side and east-west side. So this is the classification of these 7 patterns of the building, all the buildings. And we produced this configuration of the arrangement of the all the buildings. So this is the buildings model. And you can find very small hole at this level from 7 millimeters, and the diameter is 4 millimeters. There is small holes equipped of all the buildings. In that way, it will be expressed inundation inside of the building. So you can easily imagine if the water level outside the inundation water exceed this height of the hole, the inundation starts inside the buildings. And we changed three inflow discharge of the model, and we provided the inflow discharge at this point. So the flooding will start from this direction. Also, okay, the irradiation started here. And also, you can find the first, at the beginning, the inside of the building is dry, but gradually, this building, inside of the building also inundated. So blue colored border is starting to inundate inside of the buildings. This river first, the outside of the building is inundated, and after that, the also inside of the building also inundated. So we expressed this kind of process, inundation process, in the highly in residence area. So we try to express this kind of phenomena by the numerical simulations, and we compared three different models. First one is unstructured mesh model. That means we divided the whole study area into a very small triangular meshes like this. So in this way, in that way, we can express the detailed boundary of the building by the small unstructured meshes. And the next one is our Japan's central government recommendation model. So that model is recommend this kind of rectangular shaped meshes and a little bit coarse mesh. Mesh sizes are a little bit coarse like this. And using this mesh, we are recommended to introduce some vacant ratio spacing ratio or parameters. A few kinds of parameters. So in that way, we can express the effects of the buildings. And the third one is our newly proposed model, the lumped building model. In this model, the computational mesh is the same as the central government model. This size of mesh, but we introduced two different inundation depths in one computational mesh. So one is outside the building, and another one is inside of the building. You know, the water depth is different between the inside and outside of the building. So we introduced two different variables of the inundation depth of inside and outside of the building in one computation mesh. And we also calculate the exchange in discharge between the inside and outside of the buildings. So, of course, we express that the area of the building is using the vacant ratio of the same parameter of the recommended Japanese central government model. So we compared these three measures, three different numerical models, and we compared those results with experimental results. So we could find some difference among these three solution models. And we also measured the time difference of the water depth in our experiments. So at this point, the blue circle is black circle is the experimental results, and green color is the unstructured mesh model, and pink color is the lumped building model, our newly proposed model, and yellow color is the central document recommendation model. And it is difficult to obtain the how to say the same similar result of the experiments, but of course the unstructured mesh model is the most closest results of the experiments. And particularly at this point, almost the same, we obtained a very good agreement between the experimental results and the unstructured mesh model result. And we could find obvious clear difference between the central government model and our newly proposed model, between pink color line and yellow color line. So we use the similar mesh size computational measures between these two models, pink color model and yellow color model. But we consider the difference, what are the difference inside and outside buildings, and we could obtain more closer results in our by using our newly proposed model. So this and of course this lumped building model is a very efficient of the computational time. So we would like to recommend this lumped buildings model to apply to the actually urbanized area. It is very reasonable. Of course, I know the unstructured mesh model has a most detailed results, but in efficient, if we need very efficient simulation, the lumped building model is very reasonable simulation model. Okay, so this next one is the final topic. Let's start on pluvial inundation. So I explained what is pluvial inundation. That is caused by directly by the heavy rainfall. So heavy rainfall provided on the ground surface, and that water is drained through the storm drains like this. And in highly urbanized area, those storm water is collected to the sewer pipe networks like this. And if the elevation of the external river is higher, relatively higher, and that collected storm water is pumped to the external rivers like this. So in order to reproduce this kind of phenomena of the pluvial inundation, we need to have a little bit complicated simulation models. So we usually use the combination integrated model of the combination of 2D inundation flow model and 1D swap pipe network model. So 2D model is applied for the surface inundation area, and 1D model is applied to the swap pipe networks, and that is a kind of a network of the manhole and pipe. Yes. And we need to consider also the exchange interaction between the 2D model and 1D model through the storm drains. Okay, and that is a kind of difficulty to reproduce the pluvial inundation phenomena. And in our integrated model, we applied the 2D inundation flow model using these 2D shallow water equations. And these equations are usually used for the 2D inundation model, inundation simulation. And in the 1D swap pipe model, we modeled the swap network like this, the swap pipe, connection of the swap pipe and the manholes. And we can calculate the water level of this manhole using these simple continuity equations, considering the inflow discharge and the water level. And that is calculated by the bottom area of the manhole. This is continuation for manhole. And this kind of 1D unsteady flow equations are used for the swap pipe, swap pipes. And during the phenomena of the pluvial inundations, we need to consider the pressurized flow and open channel flow. We need to consider both phenomena of the open channel flow and pressurized flow. So, in order to simplify those transient phenomena, we usually use the slot model. Slot model means this kind of model. We assume this kind of slot at the top of the swap pipe. So, by introducing this kind of small slot, we can find a very, very small free surface here, even in the phenomena of the pressurized flow. So by using this kind of slot model, we can treat both open channel flow and pressurized flow by the same equation systems. So we usually use this kind of slot model for the what is swap pipe networks. And another difficulty is how to combine 2D model and 1D model. And that is also one of the difficulties of the pluvial inundation modeling. But this interaction discharge is very important because depending on such interaction discharge, inundation will happen. It is will be determined whether inundation will happen or not, and how severe the inundation depth becomes. So this is very important. And we need to consider both process of the drainage from the surface to the swap pipes, drainage process, and overflow process from the swap pipe on the ground surface. We need to consider both direction between the ground surface and swap pipes. And here we assumed where formula is and origin formula. These two equations can be applied to express this interaction discharge. And depending on this storm drain is submerged or not, we can switch these two equations, where formula and orifice formula. And also we assumed these same equation systems can be applied also for the overflow process. And of course, the positive and negative, this sign is different, opposite. And in order to validate this kind of combination integrated model, we constructed this kind of experimental facility. This is side view of the facility, and this is the plan view of the facility. And this is ground surface level, and this rectangle is the buildings, and this is the rainfall simulator. And here is one circular pipe, and flow direction is this way. And at the downstream reservoir, it has a movable gate, so we can adjust the water level of the downstream end of this swap pipe. And here's a pumping system, so we can circulate the water in this direction. So we can adjust the inflow discharge of the upstream end of this swap pipe. And this is a plan view, and you can find the roadway in the center of this basin. And on both sides, you can find the storm drain here. And this is the buildings. And at the top of the building, you can find a small hole. So the storm water provided on the buildings is drained through the analysis process. So this is a side view of the cross section of this facility. At the top of the building, you can find a small hole here. So, and this hole is directly connected to the swap pipe. And storm water on the ground surface is drained through the storm drain here. And here is a drainage box. And this box is connected by this small tube. this one is seen like this. This big tube is connecting the building and sewer pipe. And this this is the drainage box, and this box and sewer pipe is connected by this tube. So we constructed this type of this kind of facility, and we reproduced the urban inundation of the rainfall and water level of the sewer pipe. This is the photo of our facility. Here is a rainfall simulator, and this is the ground surface level. And here is a circular pipe flowing in this direction. And we can adjust the downstream water level and upstream inflow discharge and rainfall intensity. So combining these three conditions, we can set out the various experimental conditions. So using this facility, we reproduced the pluvial irrigation. So we have carried out so many cases, but today I will pick up these 5 cases. And this case 1, 2, 3, 4 is the steady case, steady flow cases. And in order to focus on the interaction between the ground surface and slope pipes, we didn't use any rainfall here. And case 1 is the open channel condition. Through the whole sewer pipe, we can find the open channel, so we have free surface. And case 2 and 3 are tangent regimes, so that means partially open channel, partially pressurized. And case 4 is completely pressurized. So we carried out these 4 cases, so through the experimental results, we determined the parameter values of the reference coefficient of the sewer pipe and some parameters for the slot models. And after that, we carried out another case. This is the unsteady case, unsteady inflow cases. So among these 3 conditions, rainfall intensity and inflow discharge and water level of the downstream end, only the downstream and water level can be changed by the temporary. So we changed the downstream water level from the sufficiently low level, and we increased the water level at the downstream end. So if we increase the downstream and water level, the whole pressurized level of the sewer pipe is increasing. Yes. And if the pressurized pressure head exceed the ground surface level, the inundation overflow started on the ground surface from the sewer pipe. And after that, we decreased the water level of the downstream end, and the pressure head of the sewer pipe will decrease. And that pressure head decreased lower than the ground surface, and the inundation water is drained back into the sewer pipe. So we reproduced such time change, temporary change of the inundation process. So this is the comparison between the experimental result and simulation results of the steady flow case. And this is open channel flow. This is top of the sewer pipe and the bottom of the sewer pipe. You can find the free surface along the sewer pipe. So using this result, we determine the reference coefficient of the sewer pipe. And this is transient. You can find a little bit free surface here and here. And this is the pressurized flow. So using this result, we determined some other parameters of the slot model. And we applied those parameters to the unsteady flow conditions. So this is the movie of the profile of the pressure head of along the swap pipe here. And we increased the water level of the downstream end here. So from now we will increase this line. We increase. And this is the inundation on the ground surface. Okay. And the water level is increasing now, and the pressure head increase also. And if the pressure head exceeds the ground surface level, so inundation on ground surface started like this. And now the water of the swap pipe is overflow on the ground surface. And after that, we decreased the water level of downstream end of the swap pipe, and pressure head is now decreasing. And that pressure head decreased lower than ground surface, and this damage of water is drained back into the swap pipe. And this is the simulation result. So we compared the simulation results and experimental results. And we measured pressure head along the swap pipes at every 1 meter. So, but here I picked up P2, P5, and P9. P2, P5, and P9. And we measured the overland inundation depth at 2 points, here and here. And smooth circle is the experimental result, and line is the simulation results. So at P2 and P5 and P9, and also I summarized these 3 points into one figure. So P2 and P5 and P9. So you can compare the simulation results and experimental results. You can find a little bit difference during this time. But around peak time, we could obtain a very good agreement between the experimental results and simulation results here. This is the time change of the pressure head along the swap pipes. And also, this is the comparison of the ground surface inundation depth at 2 points. We could find a little bit difference between these 2 points. But in the simulation results, we can find the starting time between these times, these points. But the water level was also almost the same. But if we compare the simulation result and experimental results, I think this difference would be acceptable. So totally, we can conclude we could obtain a very good agreement between the simulation result and experimental result and simulation results. So as the next step, we applied this integrated model for the pluvial inundation to the actual urbanized area to predict the inundation risk for the climate change, for example, or the effects of the flood control facilities. So we will apply our simulation model to predict such disaster prevention systems. Okay, and so in this way, so this Uchikawa Open Laboratory has a lot of facilities for the hydraulic experiments. So we usually make use of these experimental activities to the disaster prevention. Okay, that's all for my presentation. Yeah, thank you. So we have a few questions. Any question?
About the pluvial inundation simulation, have you ever considered the pluvial inundation on the mountain surface?
Steep surface.
Yes.
Sewage systems.
I am from Indonesia, and I live in the mountain actually, and my city is a city of the rain. So even in the drought season, they will rain on 3 or 4 days a week, and it's often have an pluvial inundation with the height around the 15 centimeters to 20 centimeters on the surface of mountain. So it has a very extreme slope. So have you ever considered the situation like this?
Yeah, I have never applied a model to such steep slope areas. Yeah. Yeah. Yeah, I have applied our simulation model only considering the surface flow, not consider not considering the slope pipe, hydro drainage systems. So the purpose of such our simulation was to predict the inundation caused by the debris flow.
Oh,
So not by the heavy stormwater, heavy rainfall, and we didn't consider the drainage systems. So that the phenomena is quite different.
quite different.
Okay. I think in Taiwan, some of their professors, they have did something with it's a model called SWIM. SWIM model. And SWM SWIM model, it's often used, and this model can do the modeling of steep slopes. And because next to逢甲University, we have the Dadu Mountain, and often the steep slopes have, like during heavy rainfall, all the pipes will come out a lot of waters. So we have one of our consultant companies are doing this kind of job. But I was thinking that because you did two things. One is experiment, and one is doing simulations. So the test and verification is between these two.
Yes.
So did you have any field observation to do verification? Do you have any monitor systems in the site, actual site?
I'm looking for slide. We applied our integrated model proof of pluvial inundation to the data. And here, this is one of our application study area. This area, Osaka Castle is contained in this area. And this is elevation, topography, surface elevation, and this is land use, and this one is, and pipe networks, and this is the pumping station. And we got some observation data from the Osaka city. This is the time change of the water level of the manhole. We got the data of 9 manhole data. and we compare the simulation results and observation data. About this point and this point, we obtained reasonable results. But around this point and this point, we can find some difference between the observation data and simulation data. So using this data, we calculated our simulation.
Because right now in Taiwan, the government asks every manhole we have to have observation systems. One is the depth of the water, and the second is the pressure. And we have to do it every 2 kilometers. 2 kilometers, we have to have obtain a site. But mainly the basic, the big ones have the monitoring systems, not the small one. And the city government also asks us to add analysis against trash, because trash will seize the water.
Yes, yes.
But if the water is strong, the trash will be flow away. Then it will form a surge,
Yes.
and often the surge will break the sewage system. So they ask us to recognize, okay, in some part, especially the steep one to the mild sewage system, we have to have the sitting of 2 pipe holes. You have to have a much bigger or stronger string to close. Otherwise, the surge will break the sewage system.
Yes.
So we have to do. I see one company in Taiwan has do the modeling of it, but it's very hard because often the monitor system in these manholes, they have very strange patterns.
Yes.
It's normally we verify only the maximum result, but for the jumping of the line, we don't consider it. It's very hard to model.
Yes. What is happening inside the manhole and swap pipe cannot be seen.
Yeah, many things inside manhole. trash, mud,
Yes.
a lot of things.
Trash and
Maybe sometimes leaves,
Yes.
trees.
Yes. And particularly from the Chinese students focus on the sedimentation inside the
Oh,
sedimentation.
So is in Japan, does the sewage system divide into 2? In Taiwan, right now we have rainfall sewage system and the
Domestic wastewater.
waste.
Wastewater.
We divided it too, but sometimes the pressure is too high. They combine together, they have a hole between it. So right now the sewage system, the pumping station must have a monitor during the heavy rainfall. Then it's very strange because normally wastewater you don't have to monitor during heavy rainfall. There's no water push, but due to the open for the pressure, they say it's better to do that. So that becomes the sewage system. Rainfall and has dirty water that goes into the river.
Several years ago, also in Japan, many local governments are trying to put the monitoring system inside of the manholes. And by monitoring the water level, some change of water level, if the water level of the manhole exceeds some warning level, they try to issue the warning to evacuate or something. But the how to say that time change of the water level is too sudden. Suddenly increase. So it is there is no time to issue the alert.
Yeah.
So
But
many people don't recognize that it is very difficult.
yeah, the cell will also have the jump, and it
Yes.
will break
Mm.
also.
Yes, that is a big uncertainty for
Yeah.
us. Okay.
Thank you.
Okay. Yeah, thank you very much. Okay, next, the pushing. Are you ready?
Okay, good morning. My name is Takahiro Koshiba. I'm an assistant professor at this Disaster Prevention Research Institute. Today I'm talking about really specific topic. So Kawai Sensei, Professor Kawai provided a really general talk, but I can talk about a really specific topic named experimental study on self-driving with triangular strip roughness elements for operational contamination. I picked up this research because this research little bit relates Taiwan. I will explain the reason later. And actually, I thought my presentation is just 20 to 30 minutes, so I have really sufficient time. So if you have questions, so I really have lots of time. So if you have questions, please interrupt my presentation and ask question. I have also. So first I'm going to talk about this is my table of contents. Introduction. The motivation of our study is hydraulic abrasion. Hydraulic abrasion occurs in the hydraulic structure involved sediment transport very high. So, okay, probably example is easier. This is example of hydraulic abrasion. This is observed in Koshi Dam in Japan, sediment bypass tunnel, Nagano Prefecture in Japan. So this is one of sedimentation mitigation measure in Japan. Okay, so for this explanation, I prepared another presentation because we have lots of time. So before going into self-running, let me introduce reservoir sedimentation. So I am doing lots of study, hydrology, hydraulics, sediment transport, but every study is related to reservoir or dams. So my study is very, I can say my major is dam and reservoir. Especially I'm focusing on reservoir sedimentation. So of course, what the reservoir stores not water, but not only water, but also sediment. So this is the example of a reservoir. This is just after the completion of this dam. And you don't see any sediment around here, but as time goes, I think 23 years later, 16 years later, this reservoir is suffering from sedimentation. That's here. So this part is already full of sediment. So already this reservoir is very shallow compared to the original. This is a big problem in Japan, but not only in Japan, but also Europe or Taiwan. So there are many measures against the sedimentation problem: excavating, dredging, sediment flushing, afforestation, sediment check down. But one measure very expensive measure is sediment bypass tunnel. Sediment bypass tunnel is a tunnel from connecting from the connecting upstream and downstream of a reservoir, like this red line. And when flood comes, the flood with lots of sediment is bypassed via this bypass tunnel. So the flood water does not enter to reservoir but bypass to downstream. This is simple but very effective measure against sedimentation problem. And this measure is used in Japan, Switzerland, and Taiwan. That's the reason why we hold a sediment bypass tunnel workshop every 2 years to exchange our knowledge on and research on sediment bypass tunnel. The first one was held in Switzerland. The second workshop was held in Kyoto here. And the third one was held in Taiwan National Taiwan University. And fourth one will be held in Germany this year, September. So today I will talk about self-learning, the very specific topic, but we will share the study in Germany this September with Swiss and Taiwanese researchers. Just pick up 3. I do not know how to pronounce it, but
增温水库 南华 without top.
Not this one.
The below is correct.
And in Taiwan, these 3 reservoirs have sediment bypass tunnel, and now researchers and governmental officers all over the world are watching these 3 sediment bypass tunnels, especially Himen. This one is the largest sediment bypass tunnel in the world. Okay, this is the concept of sediment bypass tunnel. Bypassing sediment radio flood to downstream during flood time like this. But because this water contains lots of sediment and water velocity is very high, the combination of high flow velocity and sediment causes bed road invert abrasion, tunnel bed abrasion, like this. This is Asahi sediment bypass tunnel in Japan. And sometimes this abrasion reaches more than 2 or 3 meters. Because once this concrete bed is abraded and completely abraded, then the base rock is abraded, and if the base rock is not strong, geologically not strong, the sediment abrade the bedrock as well. It is coarse, 2 meters, 3 meters like that. This is the contour of abrasion in Asahi sediment bypass tunnel. Water flows from upstream to downstream in this direction. One important thing is that in this curved area, curved section, the sediment abrasion is concentrated on the inner side of the curvature. This is because of secondary flow. So when curvature exists, the sediment is pushed to inner side. This is really common fact in the field of hydraulics and sediment transport, study of sediment transport. That's the reason why the inner side is abraded. So inner side is weaker, more critical in the design of sediment bypass tunnel. This is my study field, possible sediment bypass tunnel. Possible sediment bypass tunnel is around 4 kilometers from upstream to downstream, 4 kilometers. And there is a slight, very big curvature here. Just 200 to 300 meter curvature, but the length is longest in the world. Inclination is 1/50. Width of the tunnel is 6.6 and height is 7.5. This is very big, right? We can go into this tunnel by car. But as I said, Schimen bypass tunnel is probably more than double, very huge, very huge. So if you have a chance, I hope you visit Schimen Reservoir. That is very, very famous in the field of research among researchers on sediment bypass tunnel. Design discharge is 370 cubic meter per second, and the velocity reaches 20 meter per second. This is the photo during operation, but this is much less than 370 cubic meter per second, probably around 100, but unfortunately this flood causes this road, this maintenance road, to destroyed, completely destroyed. So this is just 100 cubic meter per second. The maximum design is 370, but this operation destroyed this road completely. So now the operation is not suspended, but very small scale. So, in fact, researchers in Japan, Swiss, also probably Taiwan are a little bit worried about operation of Schimen Reservoir is Schimen bypass tunnel is very huge, and discharge is also double. Something like that. This is the history of Koshibu bypass tunnel operation in the past 3 years. 2016, 17, 18. So Koshibu bypass tunnel is really new. The bypass tunnel was constructed in 2016. X-axis is time and y-axis is discharge. And blue line is inflow. This is the hydrograph. And red line is bypass to discharge. So there are just 8 operations. So there are 2 types of operations in terms of sediment bypass tunnel. So one is this type of operation. Sediment bypass tunnel is operated just during big, large floods, like this bypass tunnel. When large flood comes, the operation bypass tunnel is operated. The other type is operating sediment bypass tunnel annually, continuously. They open the, so every sediment bypass tunnel has a gate to control the discharge. This red line is controlled by the gate. The other type of operation is opening the gate continuously all over the year and discharging some amount of sediment and water. Yeah. And I pick up this operation. This is the example of operation. So black line is inflow discharge hydrograph. So hydrograph is increasing gradually, and now inflow discharge increases suddenly here. And then the operator of passive bypass tunnel opens the gate here with stepwise like 10 centimeter, 20 centimeter, 30 centimeter, like that. It's a little bit sidetracked, but the reason why they operate like this is that there is a rule, regulation in Japan for dam operation that is
Get open goes 30 minutes.
this is called 30 centimeters, 30 minutes. What it means is that it is not allowed for downstream area of downstream river of the dam to increase water level higher than this space, 30 centimeter per 30 minutes. So they cannot open the gate from 0 to 100% because if they open the gate suddenly, the increased rate of water depth in downstream reaches is more than 30 centimeters per 30 minutes. That's the reason why they are opening the gate right stepwise. And then the inflow discharge and outflow discharge, bypass discharge is almost same, and finally they stopped bypass operation here. It is called that when inflow and not inflow, inflow and bypass discharge is the same, that period is called free flow state. Free flow state. Okay, today I do not talk the detail of this model, but what I did in my PhD study was sediment transport monitoring in the bypass tunnel. So that was my PhD topic. But today I talk another topic, but let me just briefly introduce what I did in my PhD study. In my PhD study, I wanted to measure the sediment transport rate in the bypass tunnel. But it is difficult to monitor the sediment transport rate directly. Directly means, for example, using the net to catch the. Sorry, my PC doesn't. So I use surrogate vector monitoring system. Surrogate vector monitoring system is an indirect vector monitoring technique using acoustic or vibration signal for monitor the sediment transport rate, and it is used in Switzerland and Japan. This kind of technique is very common in mountainous countries like Switzerland, Austria, most part of Italy, Japan, and probably Taiwan. I think probably this is easier to understand. So surrogate vector monitoring system consists of a steel plate or riverbed on the riverbed, or steel pipe. On the backside or inside of the plate, there is a microphone or vibration sensor. So when a gravel hit on the plate, the impact is recorded as a signal like this. Just like our voice recorded by a microphone. This is very normal microphone. And then we extract the information of sediment transport rate, but sediment transport rate or grain size distribution from this signal. That was what I did in my PhD thesis. Today I do not go into the detail, but I extracted the grain size from the signal. For example, when this sediment transport, sediment bypass tunnel operation is like this, so open the gate here, and close here, and open the gate here again, and close here. The grain size, mean grain size is like this. In the beginning, the grain size is around less than 10, but when it comes to free flow, where drag force is very strong, grain size increased to 60 millimeters, and closed. And then open again and closed. There is a similar waves like this. On the contrary, beton transport rate is very constant. 0.02 cubic meter per second in the second operation. This is what I did in this thesis, but this is a little bit old study. So today I talk about my recent study, latest study on sediment bypass tunnel. So in my PhD study, I focused on sediment transport monitoring, but in the current study, I'm focusing on the mitigation of abrasion. As I said before, this is possible sediment bypass tunnel, and already the bed is abraded. So they are using many countermeasures. For example, of course they are doing regular recovery, but it is very costly. And they are also using reinforced concrete, very strong concrete, steel plate, rubber steel. Steel plate is just a steel bed made of steel. Rubber steel is made from rubber and steel covered by rubber. These two are really strong, but really expensive. As I said, possible bypass tunnel is 4,000 meters. It is impossible to cover entire areas by these expensive materials. So now we are proposing a new methodology. That is called self-lining. This method itself was proposed by Takas et al. This guy is a researcher in the government of Japan, in 1990, but that was not realized because of lack of information. His idea is installing storage. So I am not sure this Chinese character is understandable for you. But anyway, the idea is putting many obstructions on the bed of waterway. And that makes backflow, and sediment is caught into this area like this. So his idea is to he thought this area can be a cushion or soft bed, and sediment and abrasion is mitigated by covering the bed by sediment deposition. This idea sounds a little bit strange, but actually this one is used in the field of micromathematics. Probably this is more understandable for you to protect plates. So when a powder is sent to factory to factory, really high velocity. Even a small micro powder abrade, erode the pipe because of that very high flow. So they use this technique to protect the inside of pipes. And this Takasu conducted some experiments with 20 centimeter wide fluid with gradient of 150 and 100. And they checked several conditions. When they use triangular strip with this interval, sediment deposition is like this. If they use square, like this. And when the distance, not distance, interval is high, long, like this, sediment deposition is very unstable. And moreover, flow rate is very high. Self-lining is failed. So they found several knowledge on self-lining, but self-lining was not realized because they were not able to carry out sufficient number of experiments. And now there are few information, so we don't know lots of information about the experiments. So in our project now we are carrying out a basic experiment again. We are carrying out this kind of experiments again, aimed at the practical application of self-lining. Before that, I should say there are many studies on strip roughness itself. So there are many studies on how water flows where this kind of obstruction exists. This kind of study is carried out all over the world. I picked up two studies carried out in Japan. First one is study on flow patterns under different shapes of strips. One is triangular, the other is circular, right? The second one is flow pattern parallel to strip. So there are many kinds of studies on strip roughness, but there is little research for hydraulic abrasion and studies on strip research focusing on sediment deposition. And we believe that the first one is carried out by our group. This paper was written by our PhD, not our next laboratory, but a PhD student, Chinese student. He carried out the very simple self-lining experiment with using a straight channel. He used short interval of strip roughness, mid intermediate length, and long interval. And he confirmed that when interval is small, there is a vortex cell between strips. But when it comes to long distance, the cell cannot be reached this time. And there is a upward flow here. This makes the self-lining fail because even if sediment go into this area, the sediment is ejected from this area by this upward flow. So it can be summarized that it can be concluded that self-lining is failed when the interval of strip is huge, large, work flow velocity is large. That is his conclusion, and that is consistent with the study provided by Takasu et al. In 1990. And I carried out a little bit advanced study. As I said before, because the actual channels often have curved section, so I carried out the same experiment with a curved groove. I conducted the study on Michigan Laboratory here. Now we are here. There are 4 large laboratories. Number one, number 2, number 3, and number 4. I conducted this research in number 3. In a very small room. This is a curved, very small curved flume, experimental flume. This flume has a straight section here and here, and a curved section here. And I put strips like this. And I also carried out PIV to grasp the flow patterns and velocity field. So I provided laser here to an image from camera placed here. So I will explain PIV later. These are story references. This is the case where the interval is shortest. And I used grass beads to imitate sediment. I provide sediment from the upstream, grass beads from the upstream to check the deposition of the sediment. This is the experimental procedure. In the beginning, I set up the inclination and strip arrangement and start running the water. And before providing grass beads, I carried out a PIV at curved section with 3 lines, inner, center, outer, because this section is curved, so it is expected that secondary flow occurs. And secondary flow causes the uneven flow in this direction, in the this direction. And then I added grass beads from the upstream, 700 grams every 30 seconds, and wait until deposition becomes steady. Or then, more specifically, we should say dynamic equilibrium. And I carried out PIV again, and stop water and wait until all water flows out. And finally, I scanned the graph beads, the distribution of graph beads from the world to judge self-priming is succeeded or not. This is a brief experiment of PIV. We add very small powder into the water. And we provide laser from the upward. Then the powder is highlighted like this movie. PIV is particularly image velocity. This is stoic roughness. see the vortex here. And after getting this gauge, we analyze flow velocity by tracing these particles like this. This shows that water flows this way. So there is water flow. These two water flows, but also there is a big water flow to downward. This kind of flow is called sweeping. There is sweeping flow, and also vortex flow here. This technique is called PIV. And these are experimental conditions. The important factor is this lambda by d. Lambda is interval of stoic preferences. And d is height of stoic preference. So in the study of stoic preference, this parameter is commonly used. So when lambda by d is small, it means that the placement of stoic preference is very dense. Lambda by d is large, it means that the placement is very sparse. In our study, the height of stoic preference is just 1 centimeter. So lambda by d means that the interval is 4 centimeter. 12 means that the interval is 12 centimeter. And I used full number 2.4, 2.7, and 3.5. This is relatively very high full number in the study of stoic preference because we are targeting on 7 Pascal, so the full number is very high. We can say this is very marginal full number in terms of study using PIV. If the full number is higher than these values, the quality of PIV decreases, and also quality is interrupted by bubbles and the turbulence of water surface. So of course we wanted to carry out PIV with this expense higher than this full number, because in the real signal bypass standard, the full number sometimes reaches 5 or 6. But we gave up using that kind of high full number, but use these values. This is the result. First, we compared the different full numbers. The interval is fixed 8. Full number 2.5, 4, 2.7, and 3.5. 3.5. When lambda by d is fixed, the flow pattern is very similar. There are two flows parallel to the bed. This flow and this flow. This flow and this flow. Of course, as full number increases, there is a slight disturbance around here, just after the stoic preference. But basically, flow pattern is similar to parallel flows. 2 means higher than stoic preference and between stoic preference. And there is a vortex here. But when we change the stoic preference, the interval of stoic preference, the flow pattern really significantly changes. When lambda by d, the stoic preference is located really dense, there is a really stable flow. here, parallel to the bed. And also there is a cell, cell-like flow like this. There is a circulation here. It means that the flow over the strip roughness and between strip roughness is separated. But when the interval is high, the flow is really complicated, and there is exchange of water from up and down area of the strip roughness. Just after the strip roughness, water goes down. But again here, water goes up. It is high risk for self-priming because sediment is. It is good thing that sediment is transported to downward here. But the sediment transported to this area is ejected by upward flow again. And this is next I compare the flow pattern inner, center, and outer measurement lines. Because as I said before, this is curved area. There is a strong secondary flow that makes uneven flow patterns inner, center, outer lines. In the outer area, outer part of curvature, flow pattern is parallel to the flow bed. But when it comes to inner part, curvature inner part, flow pattern is complicated. There is an exchange of water from up and down. There is an upward flow here, downward flow here. I am sure this is caused by secondary flow, but still we cannot explain quantitatively. So now we are carrying out extra experiments to explain these differences. Next, I'd like to show the flow pattern of the self-priming. You can see references here and the glass beads. So in these two cases, self-priming is succeeded. The bed is covered by glass beads and the floor is parallel to the bed. But in this case, self-priming failed. So glass beads is trapped just after the strip roughness here, because of voltage here. But here, the bed is exposed. This is following the downward flow and upward flow. So this upward flow made glass beads around here ejected from the area between several strip roughness. In this case, fluid number is small, but fluid number is high here. So finally, I want to show the covering rate of the experiment. This is the result of this laser scanning after the experiment. After carrying out the experiment, I drained all the water, and then I scanned the surface of glass beads. This red area is uncovered area, and blue area is covered area. This line is lambda by d is 4. So you can see really dense arrangement of strips. Here, so lambda by d is 4, lambda by d is 8 and 12. And this column is fluid number 2.5 2.7 or 3.5. So this is mistake during the drainage in water, but we can say, in general, we can say self-lining succeeded when real number is smaller than 275, or lambda by d is smaller than 8. But we failed here. We can say self-lining failed when lambda by d larger than when lambda by d is large, and Prudhoe number is large. This is consistent with the experiment for storage channel. This is this red area is uncovered area, exposed area. Blue area is covered area. You can see the small particles on the surface of scanning result. One important thing is that the curvature starts from here. So the room is straight here. And the curve starts from here, 0 to 45 degrees. And then again, we will have a storage channel here. One result is that the inside is more exposed. So this area looks symmetry, but in this area, inside is more exposed. This is consistent with the PIB result because in the PIB result, the outside area water flow is very stable, but the inner side of curvature, there is a downward flow and upward flow. So it is expected that the outward flow ejected gas leaks around here. Another finding is that the effect of the curvature continues into the storage section. In this area, in this section, the curvature already finished. Curvature is until here, but still there is an impact of curvature. On the contrary, in this area, there is curvature, but the state of self-lining is symmetry. It can be explained by master study. For example, Ishikawa and Kim. There are many studies mentioning about this, that the secondary flow needs section to grow up. So when a curvature section starts from here, the secondary flow grows up as water flows. The curvature grows the most. The magnitude of curvature, secondary flow, reaches the peak around 20 to 30 degrees. That's the reason why the impact of secondary flow starts around here, and the impact continues after curvature finishes. In general, it is said that it takes time for secondary flow to grow up, and the impact of secondary flow continues very long after curvature finishes. So this is a conclusion that there are many studies on storage roughness, but there is few studies on self-lining, and this is the first experiment on curved channel. And the common point with storage channel is that success rate decreases as lambda by d and Prudhoe number increase. and large lambda by D result in upward and downward currents. Specific findings for curved channels are upward and downward currents clearly occur inside the curvature. That appears on the result of the segment proportion as well. And the secondary effect is the effect of secondary flow is greatest in the middle of the curvature. In the middle, not in the middle, 20 to 30 degrees of curvature. That is consistent with the previous studies. And that impact continues even after straight channel. Anyway, this project has just started, so we highly appreciate your efforts. So this project started last year, and we hope this project will continue 5 to 10 years, and self-line is applied. We hope self-line is applied to some of real reservoirs. Okay, that's all of my presentation. This is maybe measurement applied in this laboratory.
Any questions?
Excuse me. I see you choose the material for do the cell lining is by wood. right?
Good, yes, yes.
Why you choose wood to do?
Just because for this experiment, wood is sufficiently strong, cheap.
Yes.
Yeah,
So actually, do you have plan to apply it in the actual?
yes, yes.
But if it is as if it's by wood, it easily
No.
to
This is
destroy. Right?
so. We want to use steel plate or rubber steel for strip because
Oh yeah.
strip. We can easily imagine that the strip will receive very strong energy. So it should be very strong material like steel plate or rubber. Especially rubber is good. If we already know that rubber is very strong. When even when large gravel hit on the rubber is resilient and rubber makes how can I say can bounce.
Yeah, I know. But now you wood, but later you will do different material to do it. Exactly, the result is not the same. Same.
We think the result is same as long as the shape doesn't change.
Okay.
Yeah, but that is very important. So we think probably it is difficult to keep this shape in the real case because this part will be destroyed. And we think in the future, in any shape, this kind of angles are damaged and it will be like this round shape, it will be round shape.
Our school are department, last year we went inside Shimen.
Oh, really?
Yeah, we have already. And next year we will also go there too, and also in Zhengwen. And normally we can drive inside the tunnel. And I think the tunnel, due to the slope, is very steep. And they have something very similar because they want to seize the car from driving too fast. So they have the pump. The pump. It's very similar to the triangle, but it is small because they still have the maintenance car to drive inside. So the curve should not be, the bump is not so high. It's only for car to seize the car velocity, not to seize the river, the slope, and also to seize the scouring problem. But I think I did something similar in flume test just for open channels curvature, and we did it on the consolidation work.
Okay.
It's like a bar in a riverbed, but it's mostly the result is very similar, very similar, and it's very interesting that you add laser to watch the result, because I think you consider the sediment to be very fine, very small, but normally these open bypass tunnels, these sediments are in the upper region of the reservoir. So the sediment is not big, but in the upper region, the sediment is very big. They also have sometimes trees flow inside, so they have to have a gate to control it. But in three of them, they are different. One is inside the body of the reservoir, so it can be opened anytime. Nanhua is the one, because in the upstream, the sediment is mudstone, so you can see a lot of big chunk flowing, and sometimes it's stuck inside. But for Zhengwen Reservoir, it's big rocks, and Shimen is also big rocks. So these two are different. Yeah, this two is different from Nanhua's reservoir. So we are trying to find it, and also in the downstream part, I heard they were trying to do the 30 centimeters per minute, but I think normally because the channel is big, so they have warnings too, but normally they say they have to do it more than, I think it's more than 6 hours. So they consider more to let the sediment go out.
I see.
Because they have a goal to lower down the sediment level. And right now they are in Shimen Reservoir, they are using TDRs to observe different concentration and thickness of the reservoir.
I see.
Yeah, and her advisor is doing something very similar.
I see.
Yeah.
Yeah, actually I have been to Zhengwen and
Shimen.
Shimen, but I have never been to Nanhua, and I don't know
It's
lot of information about Nanha. So it writes that in Nanha the sediment is very fine.
very, very fine.
So we
Mud
don't need to worry abrasion.
Still we have to consider that.
Nanha is as large as we can enter and see the inside.
Not as big. The biggest I think is still Simen, but Nanhua I think is 5
Okay.
5 meter. Only one car can go inside. It was just finished last year. 2 years ago.
Construction.
Yeah. Nanhua.
Okay.
So I'm doing some research, but not the reservoir part, the upstream part. Yeah, so it's a little bit. They have very situations of very fine sediments inside, and all the fine sediments will scour the bed, the structure. And one question is that how do you measure the flow rate? Do you have a 450 to 600 millimeter per second speed? How do you measure that? How do you do the mapping? Like this one.
This one?
Yeah.
Or
The maximum, no, the next slide, next two slide. Yeah, this one. How do you measure the 450 and 6? How do you do that? Every one cross section measurement, or is
this is one cross section measurement
Yeah,
with
yeah.
PIV. Yes.
using PIV?
Yes.
Okay.
This is outer. So this measurement line.
Okay. So does the laser, because the fluke test is the outside is glass, so does the laser bend?
No.
No.
That is no problem. Yes.
Yeah, no problem.我们系上先前是有这个东西啊，后来那个什么王传义王老师，你们可能不认识，他有做类似的东西了。然后那时候也是在看那个结构物下面的冲刷的那个现象，后来是做桥墩呐。I explained that one of our professors did something similar, but he wanted to observe the bridge pole scouring problem. So he used laser also, and also the monitoring of each cross sections. But we use, I think it's a pipe hole, piezometer.
Okay.
Piezometer to watch how fast each section is. And it's not the PI.
I see.
Yeah.
So yes, glass wall is no problem for PIV, but in this case, little bit difficult because lots of glass beads are flowing.
Yeah.
So that makes the reflection as you said. So the quality of PIV is very low.
And also
when glass piece is provided. That's the reason why we carried out
and also,
PIV.
yeah. So we also did something very similar, is using like a pound weight meter. It's a plate, and also when the sediment goes by, we can see the weight.
Yes.
Yeah. it's a weighting meter, yeah, and but it
Low-
breaks, low cell,
yes.
but it often be struck and it's out of function sometimes, especially when the sediment is big. And the low cell will have a maximum result.
Saturated.
Yeah,
Yes.
and it breaks very often, so we did not consider using it. But recently, two of our professors are using vibration sensors to know what the X, Y, and Z is happening during because we have the structure during without water, with water, and also sand. They know the direction of the flow. So then using vibration results, X's, Y, and Z is also a way to find a different scale of sediment transportation too, yeah.
Yeah. In fact, in Switzerland, the vibration X, Y, and Z are used, but they do not use that for estimating the flow direction.
Yeah.
But anyway, these five sensors, all
Five
of
sensors.
all of them are destroyed already.
Expensive?
Not such expensive. Well, 10,000 US dollar.
10,000 US dollar.
Expensive for researcher, but not such expensive for the government.
Yeah. Any more questions? Okay. Okay.
Thank you.
Thank you.
Thank you very much.
大家好，因为我们有一段时间没有用中文报，我有点紧张。那我的名字叫张家志，今年开始是我在京大博士课程的第2年。那我的指导教授是川崎健司老师。那我之前是在成大王小文老师的水永续研究室进行我的硕士课程。那因为我的博士题目是我硕士论文的延伸，所以我今天也会提到一部分我硕士的部分。那我目前的博士题目是评估不同的气候事件和管理策略对于沿海湿地中环境因子动态的影响。那我今天的报告总共会分成4大部分。首先我会介绍一些关于我的研究背景、研究动机还有研究目的，然后再谈到我所使用的一些研究方法，还有研究流程，也会介绍我的研究区域，然后还有我现在正在进行的工作，以及我的未来的下一步，还有讨论和一些结论。那因为我的研究是跟湿地有关，所以首先我想先介绍一些湿地的基本知识。那湿地它被誉为地球之肺，它仅占全球面积约6%，却支持超过40%的物种多样性。那湿地它不仅能降低洪患的风险，同时也能提升区域的防灾韧性，并提供社区永续发展的资源，例如渔温养殖、农业灌溉或是生态观光等。因此，湿地它被视为因应气候变迁的其中一个自然解方。湿地它可以提供多种的生态系统服务。那什么是生态系统服务呢？根据联合国前几年生态系统评估组织于2005年发表研究报告中，他们将生态系统服务分为4大类，分别是供给服务，包含了食物供应、水资源的供应， 再来是调节服务，包含了防灾减洪、气候调节、水质净化等。然后还有文化服务，包含了生态旅游文化价值，以及最后一项是支持服务，包含了生物多样性及养分循环等。那事实上，全球约有45%的生态系统服务是由湿地所供应。然而近几年，随着人为活动，例如道路、工业区等工程建设、太阳能光电等能源开发，或是水坝及水闸门等水利设施的设置，而阻断了湿地的水沙来源。加上渔文养殖不当管理，还有同时也面临了气候变迁引起的海平面上升，极端降雨或是大洪水等事件，以及还有工厂、家庭废水排放造成的水质污染等问题。截至2020年，全球湿地面积已减少了约35%，这个情形也间接加剧了洪灾风险、生物多样性下降、生态失衡等情况。这些议题彰显出湿地的明智利用及管理对于灾害管控及永续发展之重要性。但问题是在人为需求和气候变迁的压力下，我们该采用哪些策略来进行湿地管理及富裕，以及我们执行了该方法后，湿地又会有什么样的变化及反应，以及是否会出现反效果，这些都是未知的。举例来说，假如有一个湿地因水源被阻断而面临了干枯的问题，我们尝试将外来水源引入湿地，然后湿地因外来水源的注入而恢复了水循环，那表面上我们解决了湿地干枯的问题，但后续却造成了湿地内水位过高，导致周遭社区在强降雨事件中面临淹水的风险。同时，因为引入的水中携带的泥沙而无法排出，造成了湿地淤积的问题。这表示，如果我们未进行充足的调查及分析，便贸然执行一些手段来改变湿地的环境，就很容易出现我们解决当前的问题，同时却产生了其他的问题。因此，我期望建立一套方法，可以预测不同的管理策略及气候事件对湿地内的各项环境因子造成的影响。接着，再透过分析这些变化来进一步评估湿地各项生态服务功能的效益。最后，我们就可以依据不同的情境下的结果及我们的目标需求，来拟定及执行不同程度的管理及富裕方法。然后这是我的研究区域，主要是位于台湾台南七股区的七股盐田。那这个盐田它在过去为全台面积最大的晒盐场，在2002年全面废晒之后，这些盐田产生的大片水域，人为湿地不仅可以作为生物栖息的替代性湿地，同时也可以提供周遭社区治洪减灾的功能。因其丰富多样的生态环境及功能，它于2007年被评定为国家级重要保育湿地。而这整个研究区域中，蓝色的区块就是湿地的范围，那绿色的点就是水门。那因为这个整个湿地它是由堤防和道路所包围着，所以是一个封闭式的环境。那湿地的水源主要就会仰赖于自然降雨，还有透过水门流入的水。那这个区域它的降雨主要就集中在每年的5月至9月，我们称之为汛期；而每年的9月至隔年2月则称为非汛期。那我们从右边的2张图可以看出，湿地在不同的降雨多寡会呈现出2种完全不一样的样貌。这显示出水是影响湿地环境因子变化的关键因子之一。那从右下图的图中可以发现，在缺乏降雨及水门未打开的情况下，湿地大多数会维持干枯的状态，而这个情况会严重限制湿地所蕴含的生态系统功能。因此，为了使湿地在缺乏降雨的情况下，还能维持其内部水位，我过去的研究是与台江国家公园合作进行了一个名为“水门引水操作”的计划。那该计划的概略就是我们选定了七股盐田湿地的一小区块作为试验场。那我们会透过18号水门的操作，将湿地外 下山溪赶潮河段的水以自然的方式让它流入湿地。那引入的水首先会经过村庄，然后排入湿地。我们希望可以利用这种富含将营养水源引入湿地的方式，有效的增进湿地各项的生态功能。然后上面两张图是引水前后的水深比较图。那我们可以从图中看出，在引水后，湿地内的水位明显的增加，同时也创造出了多样的水生环境。而在生物调查方面，在引水后，湿地内的螺贝类还有鱼类皆有增长的趋势。这些结果显示出，水门引水至湿地的确能有效的恢复湿地内的水循环，并提升栖地品质。那后续我们也根据了试验结果，我们建立了一套水门操作守则，并由当地居民协助定期打开水门进行引水。但之后的调查，之后的那个追踪调查，我们也发现，就是虽然频繁的引水的确能使湿地恢复水循环并提高栖地品质，但因湿地内的排水不易，而且溪谷地区它常年的高蒸发量，反而也导致了湿地出现了淤积及盐度过高等问题。而这显示出了仅考量单一因子的情况下，并无法完整评估的管理策略所带来的效益以及影响。因此，我目前的研究概念及流程，就是希望建立一套可以模拟湿地中各项环境因子动态的数值模式。通过数值模拟的方式，不仅可以模拟不同管理策略实施后湿地的反应，同时也可以预测各种极端天气事件对于湿地的影响。那后续再借由分析模拟的结果，我们可以评估湿地内各项生态系统功能的变化，并依据我们的需求拟定适当的管理策略。而所谓的数值模式，简单来说，就是利用偏微分方程式结合电脑演算法来模拟特定区域中水或泥沙等物质的随时间的变化量。那我使用的数值模式为川子老师开发的 Inundation Flow Model。它是一个2维非结构网格水动力模式，下方为模式中的控制方程式，包含了遵守质量守恒的连续方程式及动量守恒的动量方程式。那动量方程式中，它主要考量的重力引起的压力项以及底部引起的摩擦力项。为了验证模式的有效性，我以2020年10月实际进行的一场水门引水试验的观测资料来做模式的验证。那右上方图为水门引水操作的范围，右下方则是该区域的高层。我们可以看到，这区域整体的高层是由中向西递减。那高层中偏绿色，还有一些浅色的部分，则是道路及村庄。那当天实验引水总时间为7个小时，当日入流量在引水的第4个小时达到了峰值，大约3 cms。那模式中的网格总数为5414个，湿地的曼宁恩值我参考一些期刊文献，我设定为0.15。然后这是数值模式的结果。然后我们就来比较一下试验，我们就来比较一下那个试验结束后的空拍图，还有我模拟的模拟图。然后我们从模拟中我们可以发现，就是模拟的水流范围比实际范围大了很多，这显示出显示出模式的准确度还需要做进一步的调整。而我们可以从水深比较图可以更容易的观察。在左边的这张图中，每一块湿地都会有一个编号。那黄色点是水尺的位置，用来观测水深。而实验当天，我们每小时会记录1次水深，而我以最后1个小时的观测水深与模拟值来进行比较。而在右下图的图中，蓝色为观测值，红线为模拟值。 那我们可以发现，在湿地的下半部及靠近入流口的部分有着显著的差异。由于原本的模式主要应用于都市区域，并未考量到路渗蒸发及风引起的表面摩擦力，因此我推测这是造成差异的其中一个可能性。所以为了提高现有模式在识别准确性，目前我正在修改模式中的程式码，尝试将路渗蒸发及风力的因子编写进去。上方为模式中原有的控制方程式，下方则是我参考一些前人资料，正在写入模式的额外参数。那在连续方程式中，我额外考量了蒸发及路渗的水温变化。在变量方程式的部分，我则增加了风对水面表面产生的检应力影响。现阶段我还在修改模式中的水控制方程式，所以预计今年能完成至少水、泥沙和盐度的部分，并设计一些情境来进行模拟。营养盐的部分则希望未来如果有足够时间，也能同时纳入考量。那在模式及模拟完成后，我会依据一些参考资料来决定评估的环境指标，例如水深、水域面积、气体多样性等，还有一些我想评估的生态系统功能，包含了气体品质、防洪减灾，还有我使用的评估方法。那据我所知，台湾目前有许多湿地也都正在利用引水入盐田的方式，湿地的方式来提升湿地的气体品质，以供水用使用。例如嘉义的布袋盐田湿地、台南将军及市草的湿地，还有台北关渡湿地等。不过目前多数方法他们都仅考量到水这一单一因子，所以有可能会出现我前次提到的状况。因此，本研究尝试建立数值模式，借由考量不同的环境因子的动态，将可模拟预测不同的管理及富裕方法及气候变迁引起的各种事件对于湿地产生的影响，并透过结果进一步评估湿地生态功能的变化，希望可以提供政府或研究单位未来在拟定区域防灾规划、工程改善方法、基地保护或是特定物种富裕等相关策略时一个科学化的参考指导。谢谢。
中文啊，中文就。他们都很害羞。Because professor is behind, so I use English. First thing is that have you compared? I think your advisor, Professor Wang, has conducted a simulation model of a river 2D.
Yes.
Is also similar, I think, similar to do the modeling of watching the river flow into the wetland, and also it's good for river channels, and you can open the infiltration and also evaporation and all of the codes. You can rewrite it too. So what might be the difference between, first of all, if you have not used River 2D, it's not a question, but I think in逢甲University, some of our students have already used River 2D as a model of watching how the sediments and how the water flow reacts in rivers and also canals too. But what might be the different result of this solution? And another problem is that if you conduct a professor's model, how are you going to do the verification of the 检定验证 Okay. This result, how I'm going to measure what is the major thing that you have to check on, because normally this area doesn't have any monitoring systems, right? So that might be a very big problem. And second, like you say, the wind affects a lot, and what might be needed to correct the code. That means 2 questions.
英文还是？
Depends on you.
谢谢教授的提问。那首先我先针对教授第一个问题，就是我所使用的模式跟用在河流的模式有什么区别？首先，因为我没有实际操作过，就是使用在河流上的模式，但以我的想法上来看，我觉得最大的区别，就像可能包含它的动力方程式考量的那个考量的那个
参数，
对，它考量的参数是不一样的。例如，描述河流中的泥沙所使用的摩擦系数那些，可能会跟在湿地中泥沙的摩擦系数很不一样，所以这部分都是需要微调的部分。然后像我知道小文老师他有用一些模式模拟河流或是泥沙，那其中模式的差异还有在于可能是网格上的不一样，因为据我所知，它所使用的模式大部分是为结构网格。那在应用在水流交界面或是一些地势比较复杂的地方，非结构网格会有明显的优势。所以我想这是两个应用在不同领域的模式上的主要差异。
地表植被有被纳入吗？
目前是没有，因为我的研究区域目前植被影响不大。但如果我未来想要将这个模式去应用到其他湿地的话，可能就需要考虑到植被的影响。然后，老师的第二个问题是例如我模式中有提到会考量到
要改那个程式码。
对，要改程式码。那因为这个就是我们都有，就是有模式的程式，就是原始码，所以我其实就直接在里面去调整就好。
主要会是什么原因会造成它的这个落差的部分？因为你说是路胜跟风嘛，
对，
但会影响到，因为湿地之所以是湿地，就是因为它的水位本来就是高的。
对，是因为就像我说，就是因为这个湿地它其实在没有水源的情况下都是干的，所以我们在引水的情况下，它其实原本都是干的。
你引的是那个一般的水还是海的水？
有海水，应该算河海交界的干潮水，干潮河段的水。对，所以它进去的时候，第一个它到干的湿地就会先入渗，然后因为七股常年就是高蒸发量，所以它也会蒸发，然后再来那边的风力也很强，所以假如风顺着水的话，那就会推动水的移动速度；但如果是方向跟水的流动速度相反的话，它反而会阻碍水的流动，所以就会造成差异。
但它的湿地的水的 concentration 是不一样的，因为那个盐度会重，它会在底层。
对。
然后湿地有些地方，那个台南的王教授他们好像也有在做类似。那他是说底层的那个盐会把所有的孔隙都塞住了，所以导致你会有2层的水在上面。
对。
那这个就会在你方程式上面可能会影响。
对，所以我就是希望就是我除了考虑水和泥沙，后面我也考虑盐度的部分。那盐度部分就可以利用水作为它的驱动力来模拟它的沉淀和冲刷的情况。
孔隙率会被纳入吗？
目前我的时间上应该是没办法包含那一部分。
因为 你们老师的那个方程式，昨天在另外老师他在讲东方，里面其实有个参数是跟你那个底层的那个是有关的，所以或许它是对可能会影响的关键。
对，就是这部分它其实就是描述里面摩擦力对水流的影响，但它因为它没有考量到入声，所以我觉得空气不包含在里面。而且因为湿地的水道那水层不高，所以就是垂直向的影响我们就，
所以你就是用 Magnus coefficient 就
对，
所以你就大概是全部都均匀的，什么0.2几、0.1几这样。
对，目前就是以曼尼恩值来做调控的主要因子。
因为 River 2D 它有一个模组是可以输入底层的泥沙结构跟这个差异，你可以尝试看看。
谢谢教授，我会再就是看一下关于
因为当初是王小文老师给我们那个叶兆宪老师，刚好他一票的学生全部都在做 River 2D， 今年也有一组那个邱佩璇，佩璇就是考这个。
那在风力，就是老师刚刚提到，就是风力，我要怎么去验证我风力的影响？那其实，就是在我的研究区域中，它其实这边有相关车站，所以我就可以直接取用这个相关车站资料，用我的风力资料来做验证。
它是瞬间的风，
它是每小时记录，
就是放在你里面的话，参数会是一个平均风力吧？
平均风力，对。
你这边都吹那个南北风，南北方。
谢谢。
谢谢。没有什么好东西了，整理自己。
那我就用中文来讲一下我今天的演讲。首先做一个自我介绍，我叫韩从吉，也是来自株洲大学工学研究科传声老师研究室，现在是博士3年级在读。然后我研究的主要方向是从事洪涝数值模拟模型相关的研究。然后这也是我今天那个做的展示的主题，是 Modeling Urban Flood and Pollutant Transport, considering the building scale changes， 就是在考虑建筑物它周边环境、水流和污染物的交换的情况下，来做一个城市洪涝和污染物扩散的模拟。然后今天的展示主要从这4个方面来讲一下。首先要介绍一下这个研究的背景和目标，其次是我研究中用到的一些方程和一些数值模拟的方法，当然也是在传声老师的模型上做的一些改进。然后第3点就是一些我们做的实验，我们研究是一些学生做的实验，还有一些讨论，最后做一个简单的总结。首先是背景部分，然后我们都知道，因为全球的气候变暖，还有极端天气的原因，现在已经是一个共识。然后它们就导致了城市洪涝的频率和强度正在逐年的增强。然后由于城市洪涝造成的一些结构、房屋结构，还有人员和财产安全的一些灾害，是大家都已经熟知的。但实际上，由于洪涝而引起的2次灾害，比如说污染物的泄漏，其实它可能远比洪水本身更要危险。然后这些污染物的泄漏，就有可能导致我们一些救援工作的延迟，然后或者直接影响到这些居民的人身财产安全。就比如说下面2张图片是19年发生在日本佐贺县的一个overtopping 一个破堤事件。然后你可以发现这个污染物从那个因为水流从那个一个工厂里面带出了一些油，经过了一个居住区，然后直接到达了一个医院。然后右上面这张图片是事后在一个居民的家中拍摄的，可以明显的看到这些污染物是已经进入了这些房屋里面，造成了一些危害。然后之后我们就针对这个问题想要达成2个目标。首先是当然要提出一个2维的，就是同时考虑洪涝和污染物的一个数值模型。其次当然是要考虑这些污染物与房 房屋之间、房屋个体之间的一些流量和污染物的交换。之后是我们对这个模型使用的一些方程、分方程和一些使用数值方法做一个简单的介绍。首先我们使用的和那个刚才张家志介绍的一样，是一个三角形的非过道格子，然后是在老师使用的潜水方程上，就耦合了一个数运方程，然后可以看到第4个方程就是和刚才张家志的 PPT 有不同的地方。然后之后就是对这个控制方程里面有一些方法的使用做一个简单的介绍。首先是因为我们是想达到一个2维模型，然后希望在时空上能达到二阶的精度，所以我们需要做一个变量的重构，这也是一个通常用的方法。这个是在三角形格子上我们使用了一个就是带有一定限制的梯度的重构方法。首先我们可以看到，在左下角，这是首先我们使用就是以格子 I 为例，这周边的3个格子，根据这周边3个格子所带的所包含的保守量，先求出这个格子本身的梯度，然后再用这个格子本身的梯度以及它周围3个格子的所有的梯度求出一个权重来，然后通过这个权重和非限制的梯度，我们再用第2个 limited gradient 这个方程来求出这个格子本身受到限制之后的一个梯度，之后再用这个梯度再根据这个格子中边界的终点或者你想要的地方的一个离中线的距离，直接求出这个点重构之后的这个数值。第2个方法我们使用的是比较特殊的是使用的是一个针对水深，因为水深中我们在模拟在数值模拟中经常会遇到一个问题，大概就是它的会出现负值，以及在一些坡度变化比较大的地方会出现一些非常明显的数值不稳定。然后我们这里用了一个表面重构的方法，其实主要的思想就是根据重构之后的坡度和它周边格子，这是一个测试图，然后可以根据它这个格子修改之后重构之后的2阶的一个高度和它周边格子水深的对比。然后我们看到最左边这个图之后，曲线重构之后的坡度是相对于它左边格子来说是矮一点的，然后我们就可以利用这个重构之后的高度，将左边矮这个格子的高度抬升一点，然后抬升到右边的右上角那个格子的高度。之后我们再把相对比较这2个格子，采取一定的方法再取一个新的值，然后重复给这2个格子一个新的高程。这样的情况下，我们就可以保证这个底是连续的。然后，当然该计算的那个2个格子之间的流量通量还是照常计算的。这样的话，我们就能保证这个格子不会出现负值，就能保证在计算的情况下，2个格子之间没有太大的数值误差的出现。然后第3点，是我们这个研究中另一个关注的一个重点，就是因为我们要考虑房屋和周边环境之间水流和污染物的交换。然后这个是宽姆一个教授宽姆拉教授所做的一个物理实验。首先是我们要知道，在那个面对洪水来临的时候，这些房屋的主人通常一般情况下都是会关闭门窗的，就是防止水进来嘛。因此在这种情况下，如果门窗这些构件不会被破坏，这些水进入房屋通常是通过一些房屋上的小孔来进入的。尤其是在日本，像日本这些木质建筑和预制件用的比较多的地方，像这个图里面给出的，比如说地基上会预留一些管线用的小孔，然后门和地板之间的空隙，以及门框之间的空隙，当然还有窗之间的空隙，以及其他一些装饰物，都会导致外面的水间接的进入房屋。然后在这种情况下，我们就认为比起使用燕国公式，然后我们认为使用基于这个奥里菲斯公式和弗里彻里公式的水头差之间的，由于水头差从这些小孔进入房屋，这样来计算的话是似乎更合理的。然后基于这个理念，我们对这个方法做了一定的简化，还有我们可以给出这 A、B、C 3种不同的情况。那中间那个灰色的，我们假设它是墙壁，然后根据这个房屋内和房屋外水位的差别，以及是否能达到这个开口的高度，我们就可以利用左下角这个公式，这个奥里菲斯公式，也就是特里克里公式，进行一个简化的计算。 然后同时污染物也是根据右边的这个方程来做一个简化的计算，通过这种方法来计算出在洪涝的情况下，水流通过这些小孔进入房屋或离开房屋一个可能的流量。然后最后是一些其他的一些用到的方法，因为都是一些比较通用的方法，所以就不做展开的介绍。比如说我的坡底项用的是一种通量的方法，这样呢可以保证它与对流项可以时刻保持平衡。然后摩擦项使用了一种半隐式的分裂算法，就可以保证在面对一些极小的水深的时候不会出现非常夸张的大流速。然后时间项上也是用了盘口的预测校正方法来实现一个2阶的精度。然后之后就是对这个方法的一些验证和使用。这个介绍的是我们研究室的已经毕业的一个学生福基莫里同森和我们正在读的一个日本的学生，读博士的日本学生松井所做的一个实验。这个地方是京都市的一个街区，可能大家去过，是在那个京都的一个景点，京都御苑的对面，正对面是取了这么一个街区，然后做了一个1:100等比例模型的缩小，然后右边就是一个实验的一个概化图。这个实验装置就在这栋楼隔壁的第2实验室。然后，当然这个实验应该还在那个实验台上放，是做了一个1:100模型的缩小。然后这个模型大概的这个实验大概的运行就是从左上角那个水泵开始向一个水槽里面供水，这个上面那个水槽是3.1米长，大概有15公分高。然后等水充满这个水槽之后，就会从上面一个40厘米的开口进入这个物理模型的区域，然后这个模型就会重现这个区域，就会怎么说重现，就是模拟这个区域进水与房屋进水的这个过程。最后从下面有一个1厘米深、1厘米高的一个堰从这上面再流出这个实验区域，大概是这么一个流程。然后在P1到P88个点上是做了一个水位的测量，然后通过这个数据和我们实验模型的对比，数据的对比来做一个分析。后面介绍这张图也是当时那个福基莫里同森做的实验那张图。这个 PVC 板做的这个就是我们使用的那个缩小后的一个建筑的一个模型，然后大约是在7毫米高的一个位置会开一个4毫米的口，然后这个4毫米的口就相当于它是来模拟这个通过小孔进入建筑物的一个情况，水和污染物。但是实验的时候目前只有水做了实验，然后这些小孔是每隔40公分在这个一侧上会均匀的排列。然后这个就是隔壁的我们做实验用的实验台，就在第2实验洞里。然后下面一张图也是来自同森和福基莫里和马茨里的一个实验，是根据那个建筑物的面积、有效面积与它的边长，制作了6种不同的建筑物的模型。然后左边就是来自松井做的一个实验的一个视频，大家可以看一下，大概是5倍速的视频。对，你看一下，从那个上面40公分的小口开始逐渐的入水，这水是染色过的蓝色，可以看到一些进水的过程。大概这是其中的一个实验，对实验重复了几次，然后根据不同的入水量，也调整了不同的入水量。然后后面就是我们模型的一个模拟以及实验数据的对比。看到这是前面4个点的一个对比，因为红色的点是实验中测量的数据，但可能实验1的那个点1的测量出了点问题，是因为点1的布置的点离建筑物特别的近，所以它那个入水的水流就是入水的水流和那个建筑物受到建筑物土壤之后的水流之后会之间 interaction 造成一些波动。然后黑色的数据是我们这个修改之后提供模型的一个数据，然后那个黄色的是比较 就是大家用的比较多的一个空气率模型的数据。然后绿色的线则是一个 building block 模型的实验。它那个模型和我们模型的区别就是，他们会单独把这个建筑物的轮廓给表示出来，但是没有考虑建筑物的进水，可以跟我们的模型做一个比较好的对比。可以看到，相对于其他两种方法来说，是我们提出的模型和实验的结果，尤其是最终水深的结果，是比较达到了一个比较好的一致。当然也存在一些问题，比如说你看 P5 和 P6，黑色线就有一个明显的水深的增长率下降的一个过程。其实是因为我们考虑了那个在模拟的过程中考虑了进水，但是因为在模拟的过程中是把那个孔的面积给平均到了边长上，变成了一个平均的面积，所以导致的入水相对于实验中的入水来说要更快，来得更快、更强、更早一些，所造成了一个波动。但实际上，相对于其他两种方法来说，尤其是和 BH 模型相比，在最终水深方面还是达到了一个比较好的一致。然后之后我们是把这个模型做了一个算是一个应用在一个实际存在的部分，做了一个拓展的一个研究。这个区域是京都大学的宇治校区和它周围的一些环境。然后我们是在这个黑色三角形的点假设了一个破低的事件的发生。当然，这个因为在日本，它那个洪水事件比较多，他们有一个专门的网站叫新水ナビ，上面就是有一些就是预测了一些一旦哪个堤防发生了破低事件，可能会受到影响的区域。这些破低点和数据也是来源于那个网站，参考了一下那个网站。但是我们希望这个洪水尽快的达到我们模拟区域，所以给它了一个非常大的一个进水量，是175立方米每秒。然后模拟的实际时间是3万秒。然后在那个红色的点是京都大学实际存在的一个化学实验的一个化学品的储存的仓库。所以我们假设当这个仓库的水深达到了0.3米，那实际上这种事件是很少发生的。0.3米的时候，这个220千克的污染物会在1800秒内进入这个水中。然后右下角的图是我们实验中是我们在模拟中对一些建筑物的处理。因为我们要考虑建筑物，所以我们就依据建筑物的轮廓，采用那个三角形的格子进行了分割。然后当然是对建筑物的一些外观尽可能在保证它轮廓的情况下做了一些简化，否则的话它会有一些凸出来的门什么的，这种对于画格子来说还是太麻烦了，太复杂了。所以我们就是用5米的格子，来对建筑物这一个划分，然后在污染物扩散的周围是最多10米的格子，来进行一个区域的划分，而其他区域因为随着计算效率的影响，是最多50米的格子进行一个划分。这样的话也能尽可能的减小就是计算过程中数值误差、数值扩散带来的影响。最终这个区域我们是用82453个格子做了一个划分，然后后面是给出了一些模拟的结果，比如说上面3个图是水深。在1万秒、2万秒、3万秒变化图，下面这个图就是黑色框出来的位置，是在污染物开始泄漏后3000秒、6000秒最终时刻的一个污染物的分布情况。然后之后我们是针对这个分布情况，针对污染物是否考虑建筑物的进水对污染物扩散的影响，做了一个对比。比如说我们第一个例子是污染物开始泄漏7500秒后。在完全不考虑建筑物，只考虑地形的情况下，污染物的一个分布情况，可以看到这个污染物是比较经典的，形成了一个类似于圆，就是从高到深分布的一个比较均匀的分布情况。它的主要移动方向，主要是受水深和流速的影响。而第二个情况是考虑了建筑物，但是没有考虑建筑物之间的交换，水量和污染物的交换，也就相当于一个 BH 模型。在这种情况下，可以看到这个污染物的扩散范围是相比第一个是扩大了很多的。我们计算是大约扩大了25%的影响范围。然后也可以看到，它本身那个污染物还是呈现了一个从高到低的一个分布情况。然后第3种情况则是我们的模型就是既考虑建筑物的影响，也考虑了建筑物与污染物之间的水量交换。也可以看到，其实有相当于不少的那个污染物是被困到了那个建筑物里面的。所以我们的计 算的对比是第3种情况相对于第2种情况是减少了5%的污染物的影响范围。但是如果不考虑建筑物的里面的建筑物，里面被受困的建筑物不好意思，污染物的话，减少的范围大约达到了20%。所以说，是否考虑建筑物以及是否考虑建筑物与周边水体的水量以及污染物的量交换的话，对最终影响的结果是非常大的。所以我们认为，在一些中等规模，因为考虑到计算的效率和计算和需求的考量，是在中等规模的污染物的涉及到污染物扩散的数值模拟的话，是非常有必要来考虑建筑物这个个体它的进水对最终结果的一个影响。最后是对这个模型做了一个简单的总结。首先，这个模型是我们提出的一个2维的，考虑了刚才说的考虑了水体交换的一个数值模型。基于当然是一篇题吧，不好意思不提了。然后就是特点就是这个模型是考虑了污染物与周边环境水体以及污染物的这个交换，然后也考虑了是在一些高精度、高分辨率情况下，在从事这些复杂区域可能会受到一些急剧变化的坡度 gradient， 还有一些干湿面及小水川大流速这些影响下做的一些应对措施。然后通过了一个实验室的实验，是验证我们这个方法在计算这种我们提出这种方法，在考虑这建筑物的情况下，是一个有效也是相对精确的一种方法。最后是通过了一个假设的一个脱离实验，是讨论了在这种中等规模的污染物泄漏情况下，是否有考虑我们这些提到的这些想法的一个必要性。这就是我今天的演讲。
Any questions? No? Okay, I have. Please.
好，因为刚才第1节课的时候，川石老师也有介绍一点点那个 result 这样子啊。我蛮好奇一件事情，因为我们对就这个是这样。那因为台湾这几年也是遇到很多的淹水模拟的，就是最后跟结果差异很大。因为像刚才你讲的那个有一个老师，他们用那个窗户啊什么那个水头插那些，曾经也有人做过类似啦，但是他们后来发现实在是太麻烦了，所以我们后来像他们研究生他们都有用一个我们的第3代 third generation 的模拟是用 SoBack， 那 SoBack 的模拟其实就已经有把建筑物放进去里面，但是它的建筑物就是你要自己做 block， 那它也不管它多高了，反正就是 block， 然后下去做把那个 block 的部分就是把它的一个什么系数放进去，大概就知道它的那个 result。那但是误差比以前好大概20%到30% 这样子而已。那我觉得都还不是很好。后来我们又用了第4代，就是今年开始，应该算我们那个钟佑达钟老师他在用一个叫做 Hydro DEM， HYDEM， 它是一个1 meter times 1 meter。那你后来是说你京都大学那个是用5米的5 times 5 square 的那个 result。那我们 Hydro DEM 是0.5公分，0.5公尺，就是50公分乘50公分，很细。然后现在就是可能只能做 small section 的那个 地方，所以我们变成可能就是一个 block 这样子下去模拟。那他们也有在写类似，他是用一个 Delft University 的一个叫做 D-Flow FM 的一个部分 ，D-Flow FM 的部分现在是几乎台湾主要应该是像台湾大学海洋大学还有那个成功大学，他们都在用的主流软体啦，主流今年在主推的。那他们最后可能会变成是一个淹水的模拟的部分，但是它的淹水，它是要把 rainfall 的部分也放进去里面，但是它比较不是 input discharge 下去，它是 inflow 那个 rainfall 再加上好像新的软体好像是有把那个什么那个下水道的部分也把它，因为下水道部分有些会把它的水把它分散掉这样子，那我是觉得它还蛮有趣的哈。但我觉得我觉得最想问的应该是在你的下页，就是那个再那个水文的那个分布，对，因为在第二个，因为红色线的这个部分，红色的点的部分看起来是 measure data， 是在那个 room test 里面的吧，在那个现场的。但是你的那个绿色的 model 就是 那是 BH model 吧？
对。
BH 跟 BH model 的部分，为什么它的 curve 的部分差异的部分就这么大？尤其是在 P4 的部分，因为我们 room test 的 measure 应该通常是，我们担心的应该是高水位了 ，high head 的部分，但它的 model 的部分，你做出来好像对我们来讲，我们做防灾的会希望模拟结果高一点点 ，OK， 那 result 可能就比较 perfect， 但是 measure 就会差异很大，而且是基本上从你的第30那个 second 吧，
对
，30 second 之后开始就整个就 spread out， 像你的前面的 P3 吧。P3 那边也大概30那边就开始40秒，大概就开始有点分散。你觉得这个会是什么原因？在这么前面的 stage 就出现 spreading？
这个我们的最终的结果嘛，就是这个 BH 模型是刚才和第三代模型很像，它就是把建筑物当成一个无限高的一个
无限块，
就在那里放着。所以这种因为我们通过那个实验的时候，我们可以看出，其实有相当部分的水是进入了建筑物的里面。所以我认为就是实验的结果和那个 BH 模型来说 ，BH 模型因为没有考虑它那个水进入建筑物那一部分，所以我认为是它是因为模拟的结果也是这么说，是相对于测试的结果是要高的，而且整体的水流速和我们在看的时候和水深都是比实验结果要高的。当然老师说的也没有道理，就是我们是希望这个结果是有一个容易度在里面，然后的水深。但是我们这个实验的最终目的是为了就是看一下我们这个模型考虑了建筑物进水，完全不考虑建筑物进水是否有一个差别。然后通过我们的实验，就是通过这几个实验室看出来，如果考虑建筑物进水的话，是大概可以就是算出这一部分的差别的。因为我们看那些黑色的线和那个绿色的线来相比，尤其是 P4 是一个我们比较惊喜的点，就是8个点中效果最好的一个，就是很好的表现了这个考虑建筑物进水对水深的一个影响。当然，它这里面这个实验其实是有不少的差别。这个实验大概是几年之前做的，因为你可以看到这个水深其实是非常低的，只有几毫米。然后其实，在这种实验的话，它实验初期水深特别低的时候，我们来计算那个韦伯数，就可以得到它那个其实受表面张力的影响非常大的。对。但是随着实验的进行之后，这种表面的张力大约是10毫米水深或到20毫米水深的时候，这种表面张力，我们算出韦伯数也是才2位数。对。那种情况下是可以说是不考虑那个表面张力的影响。 所以我觉得，包括这个实验前期的一个误差，还有后面一些进水的一些误差，其实都跟表面张力是脱不开关系的。然后还有就是说的那个进水那个误差，我感觉其中一个原因也有可能是这个，就是它之所以这个模型用的是4毫米的孔洞，其实是因为前面他们做过几次实验，因为表面张力的影响，只有4毫米、3.5毫米以上，这个水能很好的进入这个模型里面，所以用了一个非常大的一个4毫米的。但是随着实验的进行，前面的数据好多的数据的前面都是非常不好看的，但只有到后面的时候，随着实验的进行，
所以它会淹超过7 mm 以上，会还会更高吗？
对，你看是7毫米，对，7毫米以上，大约最高也是10几、17、18毫米左右。
所以它会超过那个 building 吗？不会，
对，都是从孔里面进去的。
所以，但是实际上的建筑物的进来的水，除了像我们这样的窗户进来，那他不考虑，比方说是什么地下室，本来就已经有 opening 的部分，直接这样进来。因为我台湾在算的时候，我们是直接是，比方说，我家的门槛多高，它就是设input 就是这个高度这样子。
对。
所以我们是大概都设20 mm 到，那个大概就是直接那个 input， 所以它有点像 spillway 的方式 input。
对，它这个也是我们这个实验提出的一个不一样的部分，因为像老师说的，高出那个台阶的部分，大家基本上进水的话都会用验流公式，用 free flow，
对啊，
那个来算。但是像这个图你也看出，它其实下面有个通风孔，其实也相当于差不多一个地基的，在日本建筑上比较常见。但是我们在算的时候，应该也有考虑过，就是同时用验流公式和回飞速公式一起来算。但实际上最后，因为这个模拟的时间比较长，最后算出来的结果是建筑物里面都验的差不多了。其实
验门缝的方法有点像那个我们的那种像那个灌溉的那个闸门器，
水头插，
它的公式是不一样，它是用那个压力水头插，然后又射流进去，
对，
所以你的水会变成是一个 spreading 很大的一个 spreading 这样进去，但它的进来速度的差异就很大，比那个在计算不容易。
对，所以我们就有相对简化的一种方法，刚才也提到了，就是直接用这个奥利弗斯公式来做一个来求它这个边上的进入的流量的一个，
但不考虑什么 infrastructure 那些路深那些都不考虑。
对，现在没有考虑这些。
不错。大家有没有什么 ？OK， 谢谢。一样。小点，
这样进。
谢谢。
来两段一下。
Now I will take you to the laboratory, and I will show you these 3 facilities. Okay, and here the first one is a rainfall simulator, and second one is a real scale staircase model. You can check. Green tea. And third one is a real scale dual model. The first one is the rainfall simulator. Maybe our staff is preparing the 200 millimeter per hour. 200 millimeters per hour.
时雨量200。
Heavy rain.
Yes, heavy rain. But if you are elementary school children, I would recommend you can enjoy heavy rain. Yay! But the particle size, rainfall particle size is very small. it is not scared, unfortunately.
Oh. So we are elementary school.
So you're enough grown up. So please observe how to the river flood is formed by the heavy rainfall. Okay, and please imagine the catchment area of the river basin.
Yes.
Okay, so please observe that process
Yes.
of the formation, extreme river flood. Okay. So the 200 the rainfall intensity is 200 millimeters per hour, but it is not scared. Don't expect too much. Okay, the second one is a real scale model of staircase. As I explained in the morning, this staircase is assumed to be connected between the ground surface and underground spaces. And if the inundation occurred in the ground surface, that inundation water is flowing into the underground spaces, and the floor area of the underground space is small, relatively small, so the water level quickly increase. So we need to take evacuation to the higher area, but unfortunately, we can find only these staircases with flowing water. So in that case, we need to fight with flowing water. So using this facility, you can experience how difficult it is to evacuate, to climb up these staircases with flowing water. Okay. And maybe today, maybe our staff will set up the condition of the 25 centimeter overland inundation. 25 centimeter. So you can climb up. If you want, this is not compulsory. If you want, you can experience to climb up this staircase. Also, go through.
这不止25吧？你看，你看，你看，哇哦
No, weight of this dog is 50
25
kg.
吧？
But
It's a much
this
water.
water can be easily flush out. So please fight with this flowing water. If you want. Yes. Ouch. Oh, this is rescue training for firefighters.
Oh, training.
Training, yes. They are. This is the training.
里面是有救援队的消防局的。
So they succeed to rescue.
哇塞！
It's
多
really
一个人呢。
it looks very difficult to love.
Yeah.
It's a rescue training.
根本爬不上去。我觉得自己躺着最可怜，
needs help.
他已经被淹没了。
They failed.
Fail.
Yes. But don't worry, this is training.
Training.
Just training.
OK。
And he survived.
天哪！
And that one is a real scale door model. We assume the door of the underground space. Underground space. So if the water is stored outside of the door, the hydrostatic pressure is acting.
Yes.
Acting on the door. And so using this facility, you can experience how difficult it is to open the door. And you can challenge how many centimeters is the critical water depth for you to open the door. So this is photo of their experience, their training.
But if they succeeded in open the door, they will get wet, right?
Oh, don't worry, we prepared a boot. Don't worry, don't worry. Yeah, also, this one. Yeah, also this one, we prepare this type of soup.
Ah.
Don't worry about the outcome. But if you want, you don't need to use this one.
Oh.
Okay, so from now we will start here and the reinforcement simulator staircase now and finally door. I will take you this one. And please, you have belongings here, but please take your importance. Okay? And you can take photos and videos in.
冲走就是。
他有那个脸部追踪他在对战你的脸。那买啦。我又不要当 YouTube。
在录影呢。太阳大。
这个放电，那你就要改到2码，然后3号之后打爆不到。加油，各位！这个。
我做1休1啊。
这啥？传统。我们台湾叫到马扎弓啊，它是大陆在黄河在古代在治水的时候的一个方法。对。A kind of spotlight. Our construction company did this and turned a different way, and it was. 很像我们的那个，很像我们
是垂这个，为什么你们不知道
？Wrong way. You have to. 但是它是用
高度30。对，现在好像就真的30度了。现在应该就是最高度。
沙子太多，这样才会塞住。
哎，你看它下雨呀，明天会下雨，
反正是超级真的。
等一下你就会下雨了
啊！
非常推荐各位学弟妹以后来宇治实验室的时候要用走的来，很漂亮，真的很漂亮。他怎么没有上？
交流。
大驼队
交流算是一个姐妹校。都在搞水，最辛苦就是搞水。
实验室到了。超多雨伞，超多。
快杀小蛙胸部。バッテリーが少なくなる。
感觉超酷哎！我以为就可以穿23的。现在的时雨量是200吗？我也不知道哎，感好酷哦。MH 啊，靠要困湿了啦，困湿掉了啦，干。好好玩哦！好，很好玩嘞。我超不喜欢外面下雨，但是我喜欢来这边玩人工造雨。
它这边的水都在那里。
哦，好酷哦！这边水也聚集了，然后流来这里。我严重怀疑我的靴子进水， 你走过去，你走过去，
我觉得可能会进水，但是袜子会吃掉。
哦，没关系啦，来了都来了。
不然这样
啊，我裤子湿了。不要，我超狼狈的。
Water flow system?
No, the
recycle。
是有雨水吗？还是它流下来的？
Below this place, and we have a very big reservoir.
big tank.
Yeah, big tank. So we store the groundwater. Groundwater, and that stored water will be saturated using the pumping system. So this is pumping system of the rainfall separator, and layer another pumping system for our the staircase model.
So normally you don't have sediments. Right. So it's always clear water.
Yes, yes.
Observation.
Yes, yes.
Because normal sediment water will get stuck everywhere. The pipe. And also
Yes, we need to pay attention to in using the sediment.
our school has a smaller one.
看一下我们没有东西啊。没事。放假吧。
做不到，我家做不到。删掉，记得删掉。哦，是超空很想玩哦，还好，可是这个会搞到全湿哎。
24, 25.
哦，
自己选吧，要穿哪一件？
哦，这是可以穿是不是？Go. You go first. Yes.
Green picture before and after. Before.
我怕我等下跌倒哎，那公婆怎么办？公婆就摔啊。怎么样老口水？他什么意思？直接走上去哦。我觉得有沙。 觉得我做不到哎。
会不会有人被冲走？
我怕，应该还好啦，路都没有被冲走了。哎，你想抱住？抱住。好呀。就是有一股风这样子，就有点紧张哎，因为我拿 GoPro，对，要拿 GoPro 就要出哦，可以加油。可是就是我拿 GoPro 我就没办法看影片了。
这样吃吗？我想晒太阳。
不错，然后你要放在那个百货公司的厕所里面。哎、很好玩耶！现在2度了。这假的屁啦！今天那个阳光很好啊。高清高破，太棒了！
展示牌啊，
展示牌
很麻烦啊，是很麻烦。
可是就因为它是广角，所以会很难看。甜蜜蜜，没有了。
哦，不是啊。好
，Nobody know who。
放闪太阳。
哎，
放闪太阳。
我们还在那个农工部，还在跟他们，然后有个女生。
3:06，好多车。这边感觉也有一个，来这看起来是在司机。靠腰我们在录影呢，靠腰。不要说你没那么好。
Water outside you cannot walk.
Really?
I think so. I'm not sure.
You can try.
You can try. Okay, so if you want to try,
After trying, I eat ice cream time.
I want to see how much you can. 哎，换鞋啊！
每个人都要。
谁要开的？
弟弟啊，你先选。
弟弟。
你选。
弟弟。
你选。
After he goes.
Be careful there.
哎，那边水啊，小心。
哦。有啊，第一个来就会有 ice cream time。弟弟，看啊，很大哎，那口气哦，有趣哦。他按掉了是正常的。正常，你点一下。哦。铃芽之旅。铃芽之旅。太搞笑了。我在洗脚。
我阿嬷家试过50公分。
50公分啊，真的假的？
Oh, now is
30. Ray, you're 30.
Ray,
30. Okay, good.
Okay, go.
Yay!
我去那边。
Try your 30. Good. You can do 30. One hand is okay. So this door must be stainless. 40.
40 centimeter.
它水就喷进来了。 40, you can do it. Good. Let's go.
Okay. 哇，好满哦。
你塞到底哦。
不好说哦，有洞哎，有洞哎。
不行啊。我要帮你录哦。
所以男生跟女生这个例子。
没关系。为什么对？为什么才不对？
我现在都有。
You can do it now, chef. 50. How many centimeters? 50 is the final trial. 这是我们反正在哪里去？Go. You can do it. Okay, this is the final trial.
How much?
50.
好像
50. 50. 为了给好了解
30就差不多了。
好，
那
1 hand or 2 hand？对，2 hand。Sensei, impossible. You can try 1 meter. No. Okay.
50啊，很重哎。加油！啊！太重了。老师来。
Go, Sensei, go, 老姐。我只要把甩那个最有酷的地方。
老师，老师不难不行。
要有后面，对你后面要撑着，光滑掉。
哦，你要去，先站起来，然后我要换。按就好吗？对，按就好。
So, what is the record?
哦，有有。
发现一天多。
老师加油
I don't think he can.
我很怕他闪到腰哎。
好，这边点吧。Anyone want to try 16? 对啊，但没有人推过门，你也知道推不了门。 No.
Inside is 45 centimeters.
45.
推不动了，我要对速度又高。
40.
40.
From the bottom of the door.
Bottom of the door.
So, there before starting different.
那个是往外这样往外推的，这样往。
Yeah, Ray, go.
Open the door. Bye.
Directly jump into the water. Oh, easy.
Why so easy?
Why?
Why?
Easy. Okay.
台湾代表。
很轻松的，没有，它不到门的一半，它只有1/3门，可是因为它只有1/3的门。他去拿板子了。
靠腰。好了。
我们郭姓女童，
就一点点而已，有门的下半部而已。
Easy.
Too easy, teacher. 好悲惨。
大概4.5吧。
Go, Ray, your turn. 40. No, 45.
没有。
35.
40.
40.
Yeah. It's easy for Ray. It's so easy for me.
哇，至于 ，Good.
It's actually not that hard for the front line.
$40就难开了，应该过半就难开了。
50.
50.
不止哦，53. 53. 53.
Oh.
对呀，哇
Yeah, good.
53，它过半就难开了。
那他们两个好像
Slide.
会有点难。
累的屁股。
He will sleep well tonight.
Yeah.
他今天很累哦。
He is actor number 1.
Our ace.
What?
对。
Why?
对。
Why?
因为它的力量是这样子的，它就是这样子的，对啊，制衡住啦，不可能开得了。
至于台湾代表
Go go go
Go. Help!
不行了。
Help! Oh, good. 53. Slide 哦。
然后找方法，找施力点。
施力点。
对都不行。
真的不行。
哇。哇！女生代表。
还是厉害。
厉害厉害，试试看滑门啊。
没有固定可能。这个要开吗？可能要找一个人。要开。
前面他的那个
试试看啊。
看花门的那个。
不好。哦。
哇，我们仅代表日方跟你说谢谢，在此。哦，他的房子太热了，所以改变了他的那个会变，不是那种变。对。Okay, so you can find four. The entrance to the underground shopping mall. Here, shopping mall. Yes, at the City Hall. Kyoto City Hall. It's here. Kyoto City Hall. City Hall here. Oh, okay. And here is subway station. 四条那个嘛，那个是地铁站，地铁。Kawaramachi Road is Oike. Sorry.
This is Kawaramachi Road, so it's our in this road. And this is a Shakushamai. Kawaramachi
Kawaramachi Oike.
Oike. No, we still there. our inn is still there.
So this is the entrance to the underground spaces. So we can consider that in
好像在地铁站前面，就是这条是地铁，这应该是这种模拟那个盐水，对啊，逢甲大学。加油
！Just like hole.
但是它底下是那个 steel
这个的话。
这个你应该很熟悉了。
瑞元就是瑞元燕版，瑞元燕版燕。然后重点是我们那个偏差超严重。
瑞元。
那个做 S 星好帮我们写的。我那个叫你是刚廖宇君他们那主角。
Subway station here. Wow. And this is the ground surface level here. Okay. And this is the first floor of the underground shopping mall. Underground, yes. This is the ground surface. So this is underground shopping mall floor.
Oh, okay. Good.
Okay, so using through this pipe, we can provide inundation water on the ground surface, and the inundation water can inflow into the underground spaces through the staircases. And, and actually, there is another floor between this B1 floor and the subway station, but that floor is too close to the B1 floor, so that floor is how to say that, moved to over there. You can find another floor, the parking lot floor. Yes. And actually, this
subway station is directly connected to the B1 floor. And you can find the staircases over there connecting the B1 floor and the subway station. And the subway station is surrounded by the wall. Actually, for the safety of the passengers, the platform is surrounded by the wall. And only when the cars enter the stations, the door is open. So we can reproduce that opening and closing of the platform using this small plastic plate.
Oh,
okay. So using this facility, we could observe how the inundation water will spread inside of the underground spaces. And we have compared with the simulation results and experimental observation data.
So only so you can control each of the input.
Yes.
But can you all together at the same time?
Yes. Can you see over there the pipe? Okay, I will show you the final one.
Final one.
So,
好想开哦。
This is the urban inundation model. This is ground surface level. Okay, and this is building, and you can find a little bit broken rainfall simulator.
Broken.
Broken, yes. So now we don't use this one. So we have constructed this one in 2008.
Oh.
So we
20
finished,
years.
yes, the
Almost.
mission of this setup completed. Yes. Okay, and you can find circular pipe here. Circular pipe. Circular. Yes. And this is the connecting pipe with the drainage box and sewer pipe.
循环的系统。
And this is the tube connecting the sewer pipe and the building roof. Okay, and this is the piezometer, you know? Piezometer. So we can
测水位跟水压。
So using this pipe, we can measure the pressure head at each point of the sewer
压
pipe.
力水。那个寻松在1楼有做一个。
对呀、我刚刚受不了，呼吸不过来。环境。
So can
在这边，这边。来起。我。
3, 2, 1. One more. 3, 2, 1. Last. 3, 2, 1.
Thank you.
谢谢。
不然